Today I'm going to continue talking about zonotopes. And so remember, these are just Minkowski sums of line segments. So in particular, yeah, last time we gave some examples of zonotopes. This time, let me start with some facts. Facts, which I'm not going to prove, but it's nice to know these facts. First of all, this is pretty easy to prove. Each face of a zonotope is another zonotope. You can easily find this out from the definition. You know what faces of a Minkowski sum look like. It's pretty easy to see that these are all zonotopes. Another fact is that zonotopes are centrally symmetric. And by that I mean, so centrally symmetric means up to a shift minus p is equal to p plus shifted by some vector. Okay. So, and finally, the last fact is that the converse to these two statements is true in some sense. So if you have a polytope whose every face is centrally symmetric, then it's a zonotope. This part is actually non-trivial. So, and actually even stronger statement is true. So if you can just look at two-dimensional faces. If all two-dimensional faces of P are centrally symmetric, these are polygons, right? Centrally symmetric, then P is a zonotope. So yeah, in particular, so if I give you a picture of, let's see, I give you a picture of the permutohedron, you look at it and you see squares and regular hexagons as the two-dimensional faces. So these are all centrally symmetric, and so it's a zonotope. And actually, by the way, this property is sort of geometric. It's not a combinatorial property. Zonotopes are sort of, you could have polytopes which are combinatorially equivalent to zonotopes, but not actually zonotopes. All right, so again, not going to prove any of these, but it's sort of important to mention them. And what I am going to do today is I'm going to talk about zonotopal tilings. So, zonotopal tilings. And for that, so it's going to be convenient for me to introduce some notation. First of all, I'm going to start with a vector configuration. Just a bunch of vectors, v1, v2, all the way up to vn. These are vectors in R to the d. So one thing I want to do is, let me write R to the d times n. What I mean by that is I have not just a set of vectors, but a sequence of n different vectors. Each of them is in R to the d. The I is in R to the d. And unlike the previous case of point configurations, here I'm going to allow, so I'm going to explicitly allow some vi maybe to be equal to 0 or some vi to be equal to vj. I'm going to allow these degenerate cases. And then the corresponding zonotope, z sub v, is defined as the sum of the corresponding line segments from the origin to each vi. somehow I want to, you give me a bunch of vectors, and then I get a polytope. And so I want to figure out the combinatorics of this polytope in terms of these vectors. And so let me define zonotopal tilings. The definition of a zonotopal tiling, and it's going to be slightly complicated for technical reasons. Zonotopal tiling is, well, what you really should remember is that it's so a triangulation is like a polyhedral subdivision to simplices. So a zonotopal tiling is going to be a subdivision, but into smaller zonotopes. That's basically the idea. But the actual definition is slightly technical. So a zonotopal tiling of my zonotope, which, by the way, if you have an arbitrary zonotope, you can shift it so that it's of this form. So we don't really, I mean, in general, you can take arbitrary line segments between 2 points, but if you shift each of them, you can make them all from the origin. So yeah, a zonotopal tiling of Z sub V is a subdivision, which, remember, this word already has like several conditions inside of it. And subdivision C of your zonotope into smaller zonotopes. And these zonotopes have to be of the form, let me denote as Z sub I comma J. So what is Z sub I comma J is you take the sum of the line segments from 0 to VI for all I in I, and you add Vj for all j in j. So I only want to take zonotopes which use some of my line segments plus some of the endpoints. That's one condition. So here I and j are disjoint. Both of them are subsets of n. And then there is one more condition, is that, which you can forget about immediately. The condition is that if you have some zonotope Zij in your zonotopal tiling, then you have all of its faces are actually labeled by subsets of I, and so yeah, let me write it down. So if Zij belongs to your zonotopal tiling, then Z I prime J prime belongs to your tiling for all I prime subset I, and J prime subset I union J, and such that these two have to also be disjoint. Prime intersection J prime is the empty set. Yeah. No, this is just Vj. I'm shifting. So this is the zonotope. Yeah, so that's basically, this only tells me about the shift. Yeah, and so one important point that you do have to remember is that I'm not only taking a bunch of zonotopes, but I actually, for each zonotope, I also remember the I and the J that gave rise to it. Because you see that some vectors could be 0, so many different I's and J's could give rise to the same zonotope. And what I want to do is I want to sort of label each zonotope by a pair of I and J. Yeah? Well, I mean, if I wrote a set here, then the ordering doesn't matter. You're correct about that. But I want to label them by 1 through n. And I want to allow repetitions. So in a set, like, you wouldn't have repetitions. And so I and j are, let me write it down. I, j labels are part of the data. And finally, let me say that C, the zonotopal tiling C is called a fine zonotopal tiling. So it's called fine if basically all your zonotopes are as small as possible. And what do I mean by as small as possible is that if for each z ij in my zonotopal tiling, the vectors in I, vi, I in I are linearly independent. Okay, so what does this mean? This means that so the set I kind of corresponds to the line segments that I'm adding up together. And so these vectors here have to be linearly independent. And that means that all of my top dimensional tiles are sort of like parallelepipeds or parallelotopes, whatever the name in English for the. These are affinely isomorphic to cubes. All right, that's what I mean by you take Minkowski sum of a bunch of linearly independent line segments. So, and okay, so this is a long definition. Now let me try an example. Let's say I take some zonotope, and my favorite zonotope here, like two-dimensional, is going to be the octagon. I can take any centrally symmetric 2n-gon. It's all of these are zonotopes. Maybe I take this one, right? This octagon is a sum of 4 line segments. My vector configuration looks like this. V1, V2, V3, and V4. And then I can try to draw some zonotopal tiling. Maybe I draw something like this. So I have a hexagonal tile and 3 rhombi or parallelograms. So that's a not a fine, but this is an example of a zonotopal tiling. And of course, if I fill in the hexagon, then this is a fine zonotopal tiling. Right? So in 2 dimensions, fine zonotopal tilings are basically sort of tilings into parallelograms. And yeah, now I want to study zonotopal tilings. Yeah. I see. So you want me to check the extra condition for? Yeah, I have to actually label every tile. Lots of tiles, and I have to label each of them. Yeah, the J's are the shifts. And okay, so I haven't heard part of your question, so I'm not sure. All right. Okay, so let's actually try it. So let's say this is the origin. Or let's say this is the origin. Or which tiling do you want me to label? This one or this one? The top one. Okay. The origin. Okay, let's say this tile here. What is it? What are the I and J sets? I is 1, 3, 4. 1, 3, 4. J is empty. Okay. And what about this tile here? The 3. and j is just 1. Okay, and now I should look at the intersection. That's the, or should I should look maybe at the faces of the, so the extra condition tells me that the, if you have a zonotope, then I should sort of record all of its faces. Oh, actually, maybe this condition is only, yeah, okay, this condition is only for fine. Yeah, I should have, yeah, bad idea. All right. Yeah, okay, I think this condition should be true only for fine zonotopal tilings. Only for fine zonotopal tilings. Because indeed here, if this is Z134, empty set, then there is no Z14, empty set would be this tile here, which, okay, you're right. So there should be a different extra condition. Okay. Yeah, okay, J prime. That is definitely true. Yeah, okay, here's what it should be for non-fine zonotopal tilings. It should be that if you have a tile, then its faces should be labeled correctly. It shouldn't, all of its faces should be contained in my zonotopal tiling, but because it's a subdivision, but also these faces should be labeled by pairs of sets. First of all, indeed, J prime should be contained inside J. That is true. It should contain J, and also it shouldn't be for all. It should be only for those which correspond to the faces. Yeah, anyways, I know the correct condition, and the correct condition is, maybe I shouldn't tell you, or maybe I should tell you. There is, okay, so for fine zonotopal tilings, this is correct. For non-fine, the actual condition is, yeah, let me not tell you. Maybe I'll tell you next. There is, these tiles here actually are projections from the cube, from the faces of the cube, and then there's some condition on the intersection of the faces inside the giant cube, going to the intersection of the faces inside this. Yeah, anyways, let me do this next time, because yeah, it's technical. And every time I write a paper, I sort of copy this from the previous paper and never. Anyways, but what is actually easy to see is that if no vectors are 0 and no vectors are equal to each other, then you can, by just looking at the picture, you can label all tiles uniquely. And if some vectors, oh yeah, maybe I should give an example where some vectors are the same. This is V1 equal to V2, and this is V3, V4. Then my zonotope, it has double edge here. And my zonotope looks like this. And maybe if I show you a tiling, then if I tell you that this is the origin, then you don't know how to label this tile here. Or do you know what is this tile? Yeah, so this is Z14 on my empty set, or Z24 my empty set. If I just show you the picture, you don't know. But well, I could have that as well. Yeah, and the picture. Yeah, right. So then the origin would be here, and then I would. Right. Okay. So yeah, the other problem arises when VI is plus or minus. Right. Any other questions? Okay, let me erase the correct definition. And yeah, so first I want to talk about regular Zonotopal tilings. We know from previous lecture that regular triangulations are important, and now regular Zonotopal tiling. Okay, so how do I define regular Zonotopal tilings? And I want Zonotopal tilings to somehow generalize triangulation. I want regular ones to correspond to regular. So maybe first I should explain how to obtain triangulations from Zonotopal tiling. Here's a remark. Is that, so assume that you have your vector configuration, right? So if the endpoints of V1, V2, etc., Vn all belong to some affine hyperplane, to affine hyperplane H. So I want H to be a hyperplane in R to the D, but I don't want it to contain the origin. The picture should be, I have the origin, and then I have this affine hyperplane H, and my vectors they all have endpoints on this hyperplane. Then the endpoints, they actually form a point configuration. If you just look at these points, so H is basically R to the D minus 1, so you get a point configuration, get a point configuration inside R to the D minus 1, which is I'm identifying with H. And let me note, yeah, so maybe I should denote by A of A. And vice versa, right? If you have a point configuration, you can embed them in like one higher dimensional space, and then you can add the origin, and you get a vector configuration. You can go back and forth between point configurations and vector configurations. And the claim is that if I now take a zonotope corresponding to, so maybe somebody can tell me, what's the relation between zonotopal tilings of the zonotope of the vector configuration and triangulations of the point configuration? Do we get the heights? Yeah, so let me try to draw a picture. So maybe indeed, let's say D is equal to 2. So my picture, here is H, it's a line. And then my 3 vectors maybe look like this. So V1, V2, V3. And the zonotope is going to be a hexagon like this. So maybe I can try to draw. So let's say H should be green. And then maybe I can choose a zonotopal tiling of my zonotope, maybe in these 3 tiles. And somehow this should correspond to some triangulation. So my point configuration A is just 3 points on a line. A1, A2 and A3. So the claim, yeah. Oh, you want to say this somehow corresponding to regular. Let's actually even forget about regular triangulations for now. I want to make a statement about arbitrary zonotopal tiling. And let me make a statement. So the statement is that claim is that if there is a map from let's say fine zonotopal tilings of the zonotope to the set of triangulations. In general, this would be subdivisions if I drop fine. But yeah, let's say fine zonotopal tilings correspond to triangulations of A, and the map is just intersect with H. You have this H hyperplane here, and then you have a bunch of tiles inside your big zonotope. First of all, if you take the big zonotope itself, intersect with H, you get the convex hull of points in A. Does it make sense? And then each tile is like a giant cube, and then you intersect that cube with sort of you take one of those hypersimplex section of that cube with the plane, and so what you get is just a simplex. The first hypersimplex is just the usual simplex. So yeah, you can always go from fine zonotopal tilings to triangulations. Can you go back? If I give you a triangulation, can you always realize it as a section of some fine zonotopal tiling? Yeah, that's actually a trick question. I mean, it's an actual question, but the answer is no, and it's a hard problem. It's a pretty hard problem, but actually not every triangulation. There are some counterexamples where not every triangulation comes from a fine zonotopal tiling, and that's actually a question of it has to do with realizable matroids, and yeah, I'm gonna talk later about this stuff. So yeah, but the picture I want to paint is that you can always go from zonotopes to triangulations, and so in particular the regular, I want to define regular zonotopal tilings so that they would correspond to regular triangulations, and I want to define flips of zonotopal tilings so that they would correspond to flips of triangulation. As the picture, so every flip of a zonotopal tiling, if once you intersect it with H, is going to give you a flip of triangulations. All right. So in particular, yes, in this, maybe I should draw this picture here. So remember, how many triangulations does this picture have? 2. All right, indeed, one picture is, I have 2 simplices like this, and another picture is I have just a single A1 and A3. And how many zonotopal tilings does this picture have? Okay, I can reflect across, well, actually, yeah, I can draw it. I can draw the tiling upside down, but H is still at the bottom. In particular, I have a single tile, and its section is the single simplex here. All right. Very nice. So, okay, how do I define Where's the chalk? How to define regular zonotopal tilings? Any takers? What would be a natural guess? Okay, so a zonotopal tiling is regular if its intersection with H is regular. That's actually, I mean, that statement is, if the zonotopal tiling is regular, then its intersection is going to be regular. But actually, the converse is not true. So, but what I'm going to do is I'm going to try to mimic the definition of a regular triangulation. And the way I'm going to do that is, so for a regular triangulation, we chose a height for each of these points. So here, I'm going to choose a height for each of the vectors. X, a function h, height, function which associates a height to each vector in my vector configuration. Then I'm going to lift my vectors one dimension up. Vi tilde is Vi, comma, h of Vi. This vector belongs to r to the d plus 1. And then I'm going to, what do I do next? So for regular triangulations, I lifted each point to some height, and then took the convex hull. Take convex hull. No. Actual. Take the zonotope. Nice. Yeah, okay, that's actually, so take the V tilde to be the zonotope corresponding to the V tilde configuration. V tilde and then I just project lower faces. Yes, so you can actually see here I have a hexagon, right? If I lift every point inside 3 dimensions, then what I'm actually going to see is a cube. I'm going to see a sum of 3 line segments like this is going to be a cube. So, and then I sort of take the lower boundary of the cube and I project it back onto the blackboard. And these 2 pictures are like 2 different boundaries of the cube. So, and that's here the same, the construction is the same. So a face f tilde of my zonotope is lower if f is equal to f sub h of the z tilde for h d plus 1, which is less than 0. It's the same as for triangulations. And so we have a projection from r to the d plus 1 onto r to the d. Just forget the last coordinate, and then you define the zonotopal tiling c sub h corresponding to this height function h as the set of projected lower faces of your zonotope. Tilde is a lower face of the lifted zonotope. And so the claim is that this is a zonotopal tiling. CH is a zonotopal tiling of my original zonotope. And if H is generic, then this is a fine zonotopal tiling. Okay. Any questions so far? Is it completely clear or completely unclear? Should I? Clear. All right. Okay, so, and you may wonder, why is this picture so similar in the case of triangulations? I mean, there's actually, yeah, but before that, let me ask you a question. Is it true that every let's say, fine zonotopal tiling is regular? Yeah, that's actually a good question. So do we get all possible zonotopal tilings this way? Who thinks that the answer is yes? Raise your hand if you think the answer is yes. I think that the answer is no. 1, 2, 3, okay. Some people are unsure, but some people, all right. Why would the answer be no? Okay, so a lot of negativity in this class. All right. Right, I mean, for, you know from past experience that for triangulations, the answer is no. There is a non-regular triangulation. Maybe I should try to draw a picture again. So does it imply maybe that there is a non-regular zonotopal tiling? Right, we can't, all right, that's a good point. We can't always, if you give me a triangulation, we can't always realize it as a section. Yeah, so right, so in general, you can't go back, but maybe in this case, you can go back. And that's actually, I think that's true. You can go back in this case. Actually, these pictures arise in some connection to total positivity and stuff. But let me actually show you an easier picture. Let me show you a two-dimensional picture, which is going to take a while for me. Yeah, I'm actually going to draw it just over here. It's going to take a while to draw, but I'm still going to try. So, and I have to be very metric. I'm going to take 9 vectors in 3 different directions. And then I've practiced this for a while and still can't really do this very well, but let me. All right. I'm going to start with these parallelograms, rhombi, and then I'm going to do this. And then I'm going to, oh, this is bad. All right. And I'm going to connect these into what I'm supposed to see here is a regular hexagon. And then I'm going to draw this. And this is a non-regular, not a regular fine zonotopal tiling of a hexagon. That's pretty cool. Does it look like a, yeah, it looks like a zonotopal tiling. Yeah, I think I drew it pretty well. I mean, you can try it at home. It's actually, it's really hard to, how do you know it's not regular? And I'm going to tell you in a probably next lecture, but, or maybe in this lecture. Yeah, so why is this not regular zonotopal tiling? Let me explain a reason for why this is a non-regular zonotopal tiling. And since I have, okay, 10 minutes left, and okay, so let me define let me try to define objects which are dual to two-dimensional zonotopal tiling. And that is a pseudoline arrangement. Pseudoline arrangement. Again, the definition is technical, and I'm not going to give you the whole definition, but morally, it's is a collection of pseudolines. And yeah, what do I mean by pseudolines? These are simple curves in the plane such that any two curves intersect at most once. So that's the crucial condition, at most once. So you should think of a picture like this. Maybe have some curves, and then maybe these two are parallel, and then something like this is a pseudoline arrangement. And again, I'm not defining it rigorously yet, but let me say that, of course, there is a special case where each pseudoline is straight, and that is going to be called an arrangement of lines. And in general, a pseudoline arrangement is called stretchable. Stretchable if what I want to say is that you can kind of make each of these pseudolines straight without changing the combinatorics of the picture. I'm talking. No. Just yeah, each curve goes off to infinity in different directions. No, just like actual pictures that look like they could come from lines. I'm not defining it rigorously, but yeah, rigorously you would. Anyways, never mind. Let me, because again, I'm not going to talk about all pseudoline arrangements, but I'm going to talk about particular ones coming from Zonotopal tiling. So I don't have to define anything actually. But so it is, a pseudoline arrangement is stretchable if, let me just say that it is combinatorially equivalent. Equivalent to an arrangement of straight lines. Yeah, in everything here is inside R2. But I should mention that there is a generalization. There's something called pseudosphere arrangements, and they correspond to oriented matroids. So there's actually a very nice theory in arbitrary dimensions. But for 2 dimensions, let's just say, so I've defined the notion of stretchable pseudoline arrangement. So now I want to explain how to go from 2D zonotopal tilings to pseudoline arrangements. And the idea is very simple. Whenever you see so in zonotopal tilings, basically, if it's fine, then you only see parallelograms. And you replace each parallelogram by two pieces of pseudolines. You basically connect the midpoints of the opposite edges. And if you see a hexagon, then there's going to be 3 pseudolines, 3 pieces of different pseudolines, which look like this, and etc. So you just take a zonotopal tiling, and then you draw these pieces of pseudolines, and you get a pseudoline arrangement. For example, let's say I take the octagon, and maybe I take maybe even not a fine. Yeah, let's take fine first. Then I should use all of my colors to. I just start at the midpoint of some edge, and then I get one pseudoline. And here I start here, and then I get another pseudoline. And I start here, and I get another pseudoline. Finally, I start here, and I get one more pseudoline. So I get a pseudoline arrangement of 4 pseudolines. Is it stretchable or not? Hmm? All right. So I guess the answer is yes. All right. Yeah, indeed, I can try to draw each pseudoline with a straight line like this, and orange. And you can see that combinatorially, these are sort of the same pictures. So the conclusion is that this pseudoline arrangement here is stretchable. Well, and if this hexagon was empty, then you would these 3 pseudolines would meet together at a single point, right? And if I actually, yeah, interestingly enough, if I apply a flip, which I haven't told you what's a flip, but if I replace the lower boundary of a cube with an upper boundary, then my pseudolines are gonna change in a very nice way. So I sort of flip one triangular region in my pseudoline that corresponds to. From a given fine Zonotopal tiling, you're saying? Well, actually, no. I mean, if you give me a Zonotopal tiling, then I have an algorithm to draw the pseudoline arrangement. I just replace every tile with this. I connect the midpoints. Sort of, yeah. I have like an explicit map from Zonotopal tilings to pseudoline arrangements. So now let me go back to this picture, and oh, this is going to be hard. Let's say I look at this picture and I draw the pseudoline arrangement. Maybe all of these are red. You can also try that at home, and that's actually also takes some skill to quickly. Okay, I don't know if you can see anything in this picture, but the claim is that this pseudoline arrangement is not stretchable. Again, you can play with it at home. Turns out you can't really draw the same combinatorial picture with straight lines, even though if you just look at it, like any 2 lines intersect at most one point, like these 3 red are parallel and these orange are parallel, and the purple ones are parallel. But if you try to actually draw them in a straight way, you're going to run into problems coming from planar geometry. Yeah, anyways, I guess I'm out of time. So thanks, everybody. I'll see you all on Friday.